Okay, the first one. You see this program, we're talking about digital fundamental. That means we try to deal with the computer. Okay. So the first thing, basically, we have to get through very basic thing. The number system, okay, and code. First thing you know, number system, decimal number. Everyone already know. Decimal will be 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, we're using for human. And they get a 10 digit, 0 to 9. That's why they call it base 10. Okay. And the second number system, that's what we're talking about, binary number system. In binary number system, you get only 2 digits. Either they give me a 0 or they can be a 1. If they're not 1, then they're 0. If they're not 0, they will be a 1. So that's why they call it base 2. Okay. And the octal number system, they get an 8 digit. 0, 1, 2, 3, 4, 5, 6, 7. Like the decimal. But they go up to 7 only. And that will be base 8. And the last one will be a hexadecimal number system. They get a 16 digit. 0, 1, 2, 3, 4, 5, 6, 9. A, B, C, D, E, F. They get a 16 digit, so that's why they call it base 16. Okay. So basically, we're not using octal number system. Normally, in the past, in the computer, they're using both octal and hexadecimal. However, at this time, they're using only hexadecimal number system. Okay. So for A or B or C or D, any question? Basically, you understand in the computer language, in the binary. Computer inside, they understand only binary. What that means? They can understand 1, 0, 1, 1, 0, 1, whatever. That's a binary. They cannot understand the decimal. They cannot understand, anything else. However, if you type in 101101 and the computer cannot understand what you mean, but you're using the decimal that they understand. You're using the hexadecimal, they understand. How? The thing is inside the computer. Keyboard, when you're typing number 1, 2, 3, 4, 5, 6, they will be converting to this binary. So the computer can understand. Also, if you're using the hexadecimal here, you typing the hexadecimal and the computer understand what the number in the binary. The thing in the computer, they already get the circuitry. You're converting hexadecimal to binary. Okay? The thing is when the computer deal with a human, they have to using the alphabet, okay, or decimal. But inside the computer. That only thing computer understand is the binary. Now, for the binary 11011, you don't know what number. The thing is that the computer. So in order to understand, you have to converting to the binary, the decimal. So you know what the number. Okay. Now I tell you how to convert it. Binary to decimal. 11011. First thing, you take that 1 times 2. 1. Two. What power? Okay. Right now you add this point right here. Then how many bits left over? 1, 2, 3, 4. So that have to be power 4. And you adding to the next number 1 to power of 1, 2, 3. And you adding the next number 0 times 2 power of 2. Adding a next number 1 to power of 1. And the last one 1 times 2 power of 0. Then you add them up. Okay. So they come up with the number, I believe 27. 27. And they say make 10. That means decimal. Okay. So sometimes you don't have to put number 10. We know that's a decimal. So at least you know how to convert it, the binary to the decimal. Now I gave to you this example here. One, 1, 0. What decimal equivalent?
You mind if I take a guess?
What number you get?
So is
1,
it
3.
Yeah, I was gonna say 1 times 2 to the power of 3 plus 1 times 2 to the power of 2 plus 0 times 2 to the power of 1 equals, yeah, like you said, 1, 3. I could be wrong though.
1, 3. 1, 3.
1, 3. That's what
Yeah.
you got?
Yep.
13. Okay.
That means the 1101 in the binary that equivalent the same like number 13. That is I just go by at least the basic thing before you can do anything. How to convert it from binary to the decimal. Okay. However, we don't care about how to converting decimal to the binary. That we do nothing with the program. However, if you go to the college, then they will be teaching you. Okay. And I give it the example here, how to do it. You guys try. Hello.
Hello, Mr. White.
Yeah.
Ma'am. All right. Hi, good day. My name is Adam, and I'm calling from qualityinsuranceRates.com. There's some.
Okay. Now, what I emphasize here, converting hexadecimal to the binary. Okay, now if you get the number 9, what the binary? What the number 9? What the binary?
It's 1001.
Exactly. Okay, the thing is, if you can see 2 power of 3 plus 2 power of 0. 0 and 0, we don't care. So 2 power of 3 will be 8, adding 1, number 9. Okay, so basically, we given to you the table. So you don't have to convert in every time. For example, if you get the hex here and you get the binary, and also you can get a decimal, that a table will be get. If you get the binary, decimal will be 0. What binary? Binary will be also
0.
0. However, hexadecimal different. Hexadecimal requires 4 bits. 1, 2, 3, 4 to make up 1 digit. They must be 4. Now, if you get the number 1 in the decimal, and the binary will be 1, right? And the hexadecimal also be 1. However, again, they have to be 0, 0, 0, 1. And now I can give you another one, number 2. Number 2 in the binary now have to be 1, 0, 2 bit. And the hex will be 0, 0, 1, 0. Hexadecimal have to be 4 bit. Okay, and I try another one. A, that means number 10. Decimal number 10. And in the binary will be a 1, 0, 1, 0. And the hex will be A. So that is the table will be given out, telling you the equivalent between the binary, the decimal, and the hexadecimal. Okay, now, if you're looking into here, I get 9F cube base 16. That means the height. They want to convert into the binary. Very simple. Converting for 8-digit number 9, 1001. Number F 1111 and number 20010. That is converting from the binary to the hexadecimal. If you type in this binary, computer cannot understand. However, if you type in BA6 in the height, and they understand this number. The thing is, in the computer, they get a circuitry converting from this one to binary, so the computer can understand. So, when I want to make sure if you get the hexadecimal, you're able to converting to the binary. Or you get the binary, you're able to converting to the hexadecimal. If you're using your calculator, you can see they can get that to conversion for you. Okay? And the octal means 8 digits. So if you get a 472 base 8 octal, you converting into the binary. Same thing. Converting number 4 to binary, number 7 binary to binary. However, the requirement only 3-bit, not 4. 3-bit. Okay. But we're not using octal. Another code, BCD code. Binary code, decimal. When a number, letter, or words are represented by special group of the symbol, this is called encoding. If each digit of a decimal number is represented by its binary equivalent, this produces a code they call a BCD. Okay, BCD means binary code decimal. 4 bit is required to code each digit. Okay, now they given you number 874 in a decimal, and they want that to be BCD. In order to do it, converting each one, number 8, 1000, they must be 4-bit. Okay, that's requirement. Number 7, 0111. Okay, and number 4 will be 0100 in BCD. Okay, make sure when they say BCD code, you have to understand binary code decimal. If you get a decimal, you're able to converting to BCD, converting each number by 4 digits. And the next, the XZ3 code perform the same as BCD, except that 3 is adding to each decimal digit before encoding in binary. Okay, so you get a 48 number in a decimal. Okay, so basically let's see, um, except three code in here, okay? They say same BCD, except that 3 is added to each decimal digit before encoding, okay? So 0, 1, 1, 1, that means a 7, okay? We can get another chapter detail on the XZ3 code, okay? Last one, alphanumeric code, ASCII. That stands for American Standard Code for Information Interchange. If you go to the Google, typing ASCII, they will be giving you a table relation between the decimal alpha beta to the binary. For example, letter A, okay? So what bit they will be 10111101, 8 bit. Okay, that's for standard. That will be in your keyboard. When you typing letter A, your keyboard will be converted into the binary using ASCII. So that's for any computer. Now, when we're working in electronic, you're working on the circuitry. No way you can get 1 or 0. Okay? So that's why what they said here, in electronic, binary represented by the voltage or the current, but we're talking about voltage only. Okay? TTL stands for transistor logic. Okay? They define any voltage, okay, greater than 2 volts. Okay? That is 2 volts. And this will be 5.5 volts. Will be defined as a logic 1. That means when you're working on a circuitry, you're using the meter. When you measure, you get 3 volts. They will be logic 1. 5 volts, logic 1. 2.5, logic 1. That means the range from 2 volts up to 5.5 volts will be logic 1. And any voltage less than 0.8 volt to 0 will be a logic 0. Okay? If you measure, you get a 0.4 volt. So that means 0. The thing is, you not try to working with the voltage. The voltage is telling you what logic. So if I say A, I measure point A, I get 3.2 volts. What A equal?
1.
Right? That's what you need. If I get B, 4 volts, what B?
1.
What? Okay, now, when I say A adding to B, what do you think you get?
2. It's not 2.
we're dealing in digital, so you can only get
Right.
zeros and ones.
Oh, okay.
Just a minute. I mute it. Okay, now. You
Digital.
make at the point A, you get 3.2 volt. You come up with A at the logic 1. You measure B, you get 4 volt. And you come up with B equal 1. Now, if I say A adding to B, what do you think you get?
Still a 1.
The highest voltage.
1, 0.
First thing is you cannot adding 3.2 to 4. Okay? Why?
Because it's not digital. You only
More
deal
than
with zeros and
5.5.
ones.
It's more my
Okay, if you
5.5.
adding 3.2 to 4, you get 7.2, right?
Yeah.
And we don't have any number 7.
Okay, because your table say 5.5 is the maximum.
That's a high logic.
Okay.
So
Yeah, A
now,
would be 1 and B would be 1.
A1, B1, you add it.
A1
Right.
plus B, right.
If it's on the same wire, it'll only be 1, so it has to be the higher voltage. There's still a
And
1.
let's say 1 adding to 1, you get 2.
It's
In
still-
binary, you don't have a number 2.
Mhm.
But you can add in digital.
Yeah, in digital, you don't have number 2, either 0 or 1. Now I can telling you, 1 in the binary equivalent. What voltage normally?
2.5.
5 volts.
5 volt. 0 in binary. However, they will be equivalent. Right.
Mhm.
Right.
So basically in the digital system, you get only 2 voltage, 5 volt and ground.
Mhm.
When they said you connect to 1, that means you connect to 5 volt.
Mhm.
Okay, otherwise they say connect to 0, that means connect to ground.
Mhm.
So that's a very easy. Now,
Hey, Mr. Pham, can I ask a question?
yeah, go ahead.
I don't mean to get too much into this. Where you got A plus B equal 1 plus 1. When you're adding, well, you haven't gotten into it yet, but when you add 1 plus 1 is 1, and is that a carry or something?
No, that we're talking about mathematics. We're talking about logic now.
Okay, not where you do the carry.
No. When you're adding using the math, that's a different.
Okay, that's what it is.
But we not do it with
Right,
the
right,
math.
right, right. Right, I
Okay.
got you. I got you.
Yeah, we do it logic. So now, when you measure C equal 1.5 volt, what happened?
0.
Unacceptable.
Unacceptable. It's unacceptable.
Right?
Right.
They're telling you one thing. Something wrong. When you measure in the digital circuitry, either you get 0 or 1. Otherwise, something wrong with the circuit.
Mhm.
The thing is, we don't have any 1.5 volt. That's not allowed. So that's why when you build your circuitry, you testing and you measure at a certain point, you get that 1.5 volt. Guaranteed you can get something wrong. Either wrong wiring or IC not working or whatever. We don't have a that kind of the voltage. Okay, so basically, whenever you're working in the digital, you're able to get the voltage and you must come up with the logic, either 1 or 0, okay, in order to do something else. We not do anything with the voltage, okay? You cannot add in any voltage. Okay, every time, everything we get through it, you get the question, just bring it up, try to make it clear. Okay, now, you can see the next one, the waveform. Normally, on that one, they call a clock signal. You understand in your computer, they must get the clock. Okay, that means the high frequency, the cost of computer will be higher. The thing is that will be running faster. Okay, and that clock will be master clock control everything in the computer. And now, if I'm looking on that signal here, on the oscilloscope, they say this is 0. Okay? That's 0. And that goes to 1. And they keep 0, 1, 0, 1, 0, 1, 0, 1 forever. That's what normally they call a clock signal. And we're using 0, 1. However, when you measure on your circuitry, you cannot get 0. You cannot get 1. But you get a 0 volt or 0.2 volt. Or you can get 4 volt, 3 volt, 2.5 volt. That means 1. Okay? However, in the binary, we just using 0 and 1. And also you can see that this is a signal. Okay? You get 0, then you get a 1. Then you get a 0, then you get a 1. 0, 0, then you get a 1 and 1. Just the waveform. Okay? Telling you what binary combination you're supposed to get. For example, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1. Okay?
Mr. Pham?
Question?
Yeah, associated to the table that you have there, the unacceptable, low, and the maximum. So when we learn in the previous digital class about this buffer, for instance, the SN74, blah, 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 those buffers are to make sure that the voltage is going to be 5 volts when it's high, 0 when it's low, right?
That's ideal, but you not get at exactly 5. You can get 3.5 or 4 volt for logic 1. And
Yeah.
0 is not completely 0 volt. They can be 0.1, 0.2. That's to be okay.
Okay.
I have a question before you
Yeah,
move
go
on.
ahead.
I know you already said this, but I don't quite understand it. So a clock, I understand that that's a clock signal, but how exactly how exactly would you define it? That way, I could understand it for myself.
Your wire is not connected correctly.
So a clock signals when the wire is not corrected correctly, you said?
That's a hint.
Okay. Thank you.
It occurred to me that because I want you to read everybody's, and the reason you need to is because you're going to form your research group.
Who said it? Anyone say something?
To get going.
No, I'm good.
No, okay, I mute it. Okay, next one. Did you get only one? 0 to 1, then go down to 0. That's what they call a positive going pulse. 0 go to 1, then go back to 0. Okay, and the S going 0 to 1, they call a rising or leading S. Okay, and the one going from high to low, they call a falling or trailing S. That's just a definition. Okay, you get the going 0 to 1, they call leading. From 1 go to down to 0, they call a trailing S. And the same thing here. Okay, high go to low, that means falling. Okay, and 0 to 1, that's rising. Okay, this is a negative going pulse. Okay, they can go from high to low, or they can go from low to high. Okay, so this is what we need. Okay, high to low, negative going. This is low to high, positive going. Okay, a portion of periodic digital waveform. Okay, the measurements are in milliseconds. They want to know period, frequency, duty cycle. Okay, now they given you this signal here. They want to know the period. You understand this will go up. Okay, and we have to looking for when they go up again. So this will be one period or one cycle. Okay, and they go up and they high for a while here. That's what they call a DW. Okay, that means the width. Okay, and also this is the width in here. In order to calculate the duty cycle, you take the TW divide to T and time 100%. Okay, now if I get this signal, okay, so what T? Okay, and also TW, the width. Now you can see from here to here, how many percent?
100%.
100%. Complete for one cycle. And that's why you can see from TW here, you get 50. And this 50. Okay. So that's what they call a 50% duty cycle.
Mr. Friend, question?
Yeah, just a minute. Yeah,
Isn't that determined on the strength of the signal and the consistency of the signal so that you know what 100% signal will look like, meaning that it repeats consecutively, and then you can determine what signal you want to look at, and then that will determine how you could calculate your duty cycle? Don't you have to have a fairly stable signal in order to apply percentage?
okay. For example, they want you to draw 50% duty cycle. Then you must be draw this one. 50 are here and another 50. Okay. Now, on this one, how many percent you take? On that one. You
Maybe
can
like 90%.
Complete 100.
how many percent duty cycle for this signal here?
Maybe 10%.
No, like 90%. 10%? Okay.
The thing is, they're supposed to be 10. They're supposed to be
90.
90. Depending on TW. But normally, interview you will be hit. They just say, okay, I want the signal 50% duty cycle. Then you're able to draw 50%. Or they say, okay, I want 10% duty cycle. You're able to draw it.
And Mr. Pham, my
Yeah.
question is okay, on the smaller one, you wrote 10. Then on the bigger one, you wrote 90, but above that, you wrote 10%. Isn't the small one 10% and the big one 90%?
For sure. You can say from here to here. 100%.
Right.
And that only get a 10. And the rest here have to be 90.
Okay. So where you wrote that 10% at up top, what is that?
They're telling you the width of this one here.
Oh, you were referring to that one. Okay.
Right. You have to know the TW.
Hey, Mr. Pham,
Yeah.
the reason to choose, for instance, a 10% duty cycle or 50% duty cycle is to optimize the power consumption. Is that the reason?
No, the thing is, one cycle, that's 100%. And now you want to know duty cycle. You must know the TW, the width of the signal. How many percent? For example, on that one, I estimated, not exactly. I say, this is a 10. And the rest have to be 90.
Yeah. No, I understand those numbers, but I'm trying to think. For instance, if we have a TW, that is a short period of time that the signal is going to be high, short period of time, this means less energy. The system consumes less energy because the signal
No. Who cares? Depending on application.
Okay, so it doesn't care.
Yeah, doesn't care. Does not affect anything. Only thing is when you see the signal, you're able to know what is the duty cycle. So
Mr. Pham,
you must know TW.
Mr. Pham, I guess what some of the other students are asking, maybe, I don't know if it's the same as what I'm asking. what is duty cycle? What does it represent? What is it? If we know the duty cycle, what does that tell us? What does it tell us?
That's telling you how the signal will be look like.
Questions?
If they given you 50% duty cycle, then you can see how the signal look like. If they
Oh,
say,
so you're saying it only describes the signal. It describes the signal, and that's all it does. In
Right.
other words, on one side it's 50%, on the other side it's 50%. But if it's one side is 10%, the other side 90%, then it's describing it that way.
that's a for the signal.
All right.
If
Okay,
they-
thank you.
If they asking you, okay, draw for me 30% duty cycle, then TW will be 30 and the rest will be 70.
Now, what effect does that have on the way the circuit is working? Or
Right, depend. Cannot be telling you what circuitry. Okay,
Question, Mr. Brown? Question, Mr. Brown?
yeah, go ahead.
Kind of applies to both Marcelo and Joe's question for the circuit. Say in manufacturing, the engineering has a final test and they have the duty cycle, and the test result goes along with the product and it shows a consistent duty cycle, right? And say a component or a board returns and you hook up the oscilloscope to see if the duty cycle is consistent. Can the duty cycle determine the location of the component based off of the phasor angle or the signal disruption? Can't it locate the component that might be out of tolerance or failing?
No, now, for example, 10%, 90%, okay? 10% duty cycle. What that mean? That means the signal going to the circuitry, they want to be high only certain time, and they must be low, depending on they given to you the time, okay? For how many 100 millisecond, then 10%, okay? If I say from here to here, 100 millisecond, easy to understand. So they want the high only 10 millisecond. Then they have to be low for 90. That depending on the circuitry they design. How long they want it to be high. How long they want it to be low. However, on this one, I just bring it up to you. How do we calculate the duty cycle? In one period, they want to know how long they be logic 1, how long they will be logic 0. Normally, when you see the clock signal, they will be 50% duty cycle. Okay? They're telling you the clock right here. You see that?
right.
50 high, 50 low. Okay? And on this one, that's a different. But most of the clock must be the same, 50% duty cycle. Okay, that's a very, very basic thing. We need to try to help you to understand. Now, in here, you get 2 ways to transfer the signal. One will be a serial data. One will be a parallel data. Okay. For serial data, they say 8-bit. Okay. 1, 2, 3, 4, 5, 6, 7, 8. 8-bit. They need only one wire. Okay. You go to the receiver. They're telling you the signal transfer will be look like 1 then 0, 1, 1, 0, 0, 1, 0. They keep going, depending on how many bits. However, they need only single wire for serial data. Now, this is the same thing, 8-bit. However, they're using parallel data. So parallel data 8-bit, you need one wire for 1 bit. Okay, you get 16 bit, you need 16 wire. You get 32 bit, you need 32 wire. Okay, now where they using parallel here, data transfer in parallel, where? In what circuitry, in what machine, in whatever. They must be using parallel, not serial. If you don't know, I am telling you, in your computer.
Printing.
Only the thing happen in your computer will be parallel data. So that's why when you go to buy the computer, they can ask you 32-bit, 64-bit. You see that? 64-bit, they need 64 wire. 32-bit, they need 32 wire. In the past, they're using 8-bit, 16-bit. Or not, that must be parallel data. Computer cannot understand the serial. So where you see the serial data? In what device?
USB.
In what?
Telephone.
Telephone. The cell phone. Telephone.
The
Okay.
Christmas tree lights.
The thing is when they're talking, you're talking too much, that means too many bits. You cannot get too many wires to cover. So that's why they have to be serial data. And that we bring it up to you one thing. When they transfer the data from one place to the other place, they must be using serial data. When you go to the banking, same thing. Okay, you deposit, they can type in any money value you enter. And that data have to get sent to the central computer. And they must be using serial data.
Mr. Pham, can we do the interpretation that serial data is slower in speed than parallel data, but the parallel data needs more wires, so is in some sense expensive from a physical perspective?
Serial data, for sure, they will be slower than parallel data, for sure.
Okay.
The thing is, you get 8-bit one at a time transfer.
Okay, okay.
Parallel, they transfer 8-bit at the same time. They faster. Okay. However, I'm telling you. They cannot design anything working with the serial data. Okay. When the wire go into the phone, inside the phone, they will be using parallel data.
Mhm.
The data transfer into the computer. Normally they're using serial. However, when they go into your computer, they have to converting serial to parallel data so the computer can be working on. Computer cannot working with a serial.
Mhm.
So now that to bring it up for you, you get two different types
Mhm.
of data transfer, either serial data or parallel data. In any machine inside, they must be parallel data. Okay. However, the data coming, they can be serial, and then that serial must be converted to the parallel. Okay. We not design anything with a serial, just parallel. Okay, any question? Easy, right? Okay, now you can see this is a table given to you. How many bits here? Normally you can get 1, 2, 3, 4. Okay, so this is telling you the decimal number. Okay, and this is a binary number.
Mhm.
0, then you get 0. 1, 0, 0, 1, 2, 1, 0, and 1, 1, and so on. Number 15, and you get 1, 1, 1, 1. Okay, so they say here, the largest decimal number equal to power of n equal 1. N will be number of bits. If n equal 4 bits, then the maximum decimal equal to power of n minus 1 means 2 power of 4. And that will be 16.
minus 1.
And that's why you get 50.
Decimal. Max.
If you get a 4 bit, then the maximum number you can get will be 15 decimal. That's how come you get here.
Because, hey, Mr. Pham, because really we count 0, right?
Right, we start from 0 in binary.
Mhm.
So if you count 0, it's a total of 16.
Right.
Mhm.
So if you get a 4 bit,
Maximum.
the maximum number will be 15 in decimal. Okay, now if you get 3 bit, what is the maximum
Maximum data.
7.
in decimal? 3 bit.
8.
Come on.
7.
7. 2 power of n minus 1. N equal 3. 2 power of 3 means 8 minus 1 will be 7.
What do you need?
And now if you get 16 bit, then you have to do 16 bit. 2 power 16 minus 1. That means in decimal. If you're using your calculator, And you can get the number, I think 6,500, 535. Okay? That is the way how to find the relation between the binary and the decimal. Now let's see. Basically, encoder. This is your calculator. That's what we call encoder. That means you typing number 9, that will be decimal, right? When the number 9 inside your keyboard, you get this IC. Number 9 will be converting to 1, 0, 0, 1. That means binary. The thing is, computer cannot understand number 9. They understand 1, 0, 0, 1.
So Mr. Pham, a question. So whether it's a telephone or some other device that have a number pad, every time you hit, like, say, a 9 or 8 or 7, in this case, a 9, you hit 9, and then inside the circuit, it shows 1001.
Exactly.
And so as you go through, like, your telephone numbers, 619, whatever the number is, it
They have to
changes.
convert into binary for each one.
Okay, yeah, okay.
The thing is, everything inside calculation or computer, they don't understand number 9, but they understand 1001. So that's why they need encoder. That IC, whatever you're typing in, they send it out binary. Okay? And now this what they call a decoder. The opposite. You send the binary number 8, 1, 0, 0, 0. Number 8. That means the computer send it out 1, 0, 0, 0. Then now output of the decoder will be connected to the display segment. Okay? They display number 8 for you. If you say you sending a computer sending out number 9, 1001, and in here they will be display number 9 for you. Okay, so basically that for the human and this for the computer. So you try to understand between the decoder and also encoder. Encoder the converting decimal to the binary, and the decoder they converting binary to the decimal. However, they need to segment. That's what they call a 7 segment to display, so you know what the number or what the letter A or B or C or D.
Hey, Mr. Pham,
Yeah,
in that case, in that example, can we say that just before the decoder, we have a serial signal, and after the decoder is parallel? Can we say that?
after the decoder.
Parallel.
Now, the thing is, depending on the IC,
Okay.
data have to be parallel.
Okay.
If you're looking on the segment here, basically, how many segments? 1, 2, 3, 4, 5, 6, 7. 7 segments.
Mhm.
Each segment, they get the diode at it. For example, this they connect to route. So for the segment, this I say A, for example. You want to turn it on, you apply logic 1. Turn it on. Okay. So each segment you get 1 diode. So depending on what letter, what number, they turn on, turn off diode.
Okay.
Example, you get an A here, B, C, D, E, F, Z. If you want the number 9, they turn on A, on B, on C, on G, on F. Okay?
Hey, Mr. Pham, a question.
Yeah.
The encoder and the decoder, is one of them used more in receive? Which one is used more in receiving and which one is used more in transmitting?
No, nothing to do with transmitting.
Only receiving?
Depend. If you want to converting from decimal to binary, then you're using encoder. That's just the one I see. You apply input by decimal. They given you the binary output.
Okay, so I guess what I'm asking then, okay, so neither one of them are used, they're both basically used in receiving.
Right, receiving binary or receiving decimal.
Okay, but no transmitting.
No, not anything to transmitting.
Okay,
Converting binary to decimal or decimal to binary.
okay, thank you.
Okay, so what I need, okay, this will be talking about binary to decimal conversion. That means if you get this binary and you turn it into decimal, I given you the answer here, but I try to repeat it. You take number, first one times 2 power of 1, 2, 3, 4, 5, 6, and add them up. That will become up to this one, okay? And convert the following decimal to number binary. I don't care that one, okay? We don't using that, okay? The thing I prepare to next meeting, binary addition. If you get 0, adding 0, you get 0. 0 adding to 1, you get 1. 1 adding to 0, you get 1. 1 adding to 1, you get that. Get what? You get 0.
0
However,
carry 1.
You carry 1. Next meeting, I explain to you how they work. Okay, this binary subtraction. Go through that two part. Okay. Then this one we'll be talking about what inside the computer in order to do with positive and negative. You can get number 5. Number 5 means 1, 0, 1. However, if I want -5, what can I do? How the computer do it? Okay, so that's why we will be learning in either system built inside the computer to take care of the negative number. That's what we call a first complement or second complement. Either one, not both. Most of the computer using second complement system. That means that that system try to deal with a negative number. Okay. For example, you get 101, that number 5 in a decimal. However, if I say I want -5, that have to using complement, second complement. Okay. So normally you get lecture with me one day. Next week still went on Wednesday. Next one will be 2 days. However, after next week, then take one on Monday, take 2 will be on Tuesday. On Wednesday, Thursday, Friday, that will be the lab for either take 1 or take 2. So when we given out the lab, we're telling you what needs to be done. And when you're talking to Sam, he's supposed to give to you on off the part, on off the wire, the board you need to buy. Okay, we'll be telling you what the board, how they look like, how to build the circuitry, and also how to test when you connect into the system box. Okay. Some people for a long time they in the program, they already bought the box. Now we don't have it anymore. Before I still young, I can build. Now I get older. So especially if you want to run at home, we can let you borrow for 1 day, 2 days, or 3 days. So you can run it at home. However, if you run at home, you don't have equipment to troubleshoot it. If they fail, you don't know how to fix it. My job will be teaching you. When you run it, it failed. I will be telling you what needs to be done to fix the problem. That's what they're talking about, troubleshooting. Okay?
Mr. Pham,
Any question, anything?
question.
Yeah,
Are you helping locate breadboards?
help you to what? Get a breadboard?
Are you, yeah, can you still assist with buying a group breadboard?
Yeah, I don't know. I have to go back into the school. The thing after 2 years, I don't know what I bought. Everything in the class. Okay. So
You're saying you don't know how many extra breadboards you have, right?
right, I don't know. Okay. So after next week, I can go to the class and check to see. Okay. Otherwise, I can buy it. And only thing is, if I buy it, that cost you $20. If you go to the what?
The breadboards, if you buy them by yourself individually, they're like 30, 40 bucks. But what
Yeah.
you're saying, and what you and Lowell saying, by getting them as a group, you can get a cheaper rate.
Right, 20.
Hopefully.
You buy it electronic store cost you $45.
Hopefully, Mr. Pham, because it's inflation now, prices went up.
Yeah, I will be find out. I still left over, otherwise I have to order. Only thing you have to tell me who want it, then I order maybe 10, 20. Okay? So that will be cheaper.
I won 2, Mr. Pham.
Okay, I try to figure out. Okay? And next week, hopefully can get no, maybe after next week. The thing is, after next week, we return to the class. I support you. Then I can take everything and let your guy know. Okay? Like, Mr. Smith, they already get also the system box at home. He can build, he can run. No big deal. That's easier. Lab one, then you must get into the lab to do. However, digital lab, you don't have to. Easy to get through the digital course for Tech 2. Okay, any more questions? Anything else? If it's not, okay, then good night, everyone.
Right.
Thank you. Good night.
Thank
Good
you.
night.
Have a good,
night.
have a
Thank
good
you.
weekend, okay?
Okay, bye-bye.
Bye-bye.
See ya.
Okay, well,